Okay, welcome everybody to this Laws of Nature seminar today. And today's speaker is Dustin Lazarovici from the Technion in Haifa in Israel. He is a philosopher of physics and also from his past, at least a mathematical physicist. He obtained a PhD in both philosophy and mathematics. Today, he's a senior lecturer on philosophy of physics, and he will speak today about the question why the book of nature is written in the language of mathematics. And maybe one word before we start. So the modalities are as follows. We have about a 1 hour talk and then maybe 15, 20 minutes questions. And yeah, if you have a short question, you can ask in between, and otherwise, please postpone it until after the talk. Okay, so thanks, Dustin. Please go ahead with your talk.
Okay, thank you very much for the introduction and of course for the invitation and for putting this very exciting lecture series together. So the talk that I'm giving today is based on an essay that I contributed for a memorial volume for my teacher and mentor Detlef Dürr. So I'm going a bit out of my usual comfort zone, so to talk a bit about ancient philosophy and history of thought, but I thought it is a topic that is very fitting for, well, laws of nature, or lecture series called Laws of Nature. Since the question is why the laws of nature, as far as we have discovered them, are written in the language of mathematics. Right? And of course, the title of the talk is based on a famous quote by Galileo Galilei, where he said, philosophy, he means here natural philosophy, is written in that great book which ever lies before our eyes, I mean the universe. But we cannot understand it if we do not first learn the language and grasp the symbols in which it is written. This book is written in the mathematical language, and the symbols are triangles, circles, and other geometrical figures, without whose help it is impossible to comprehend a single word of it, without which one wanders in vain through a dark labyrinth. So maybe we can already take note, except from the fact that it's a beautiful quote, that he's talking primarily about geometry, and geometrical figures. Paul Dirac, in a very nice essay in American Scientific, formulated a similar feeling as follows, saying, it seems to me to be one of the fundamental features of nature that fundamental physical laws are described in terms of a mathematical theory of great beauty and power, needing quite a high standard of mathematics for one to understand it. One could perhaps describe the situation by saying that God is a mathematician of a very high order, and he used very advanced mathematics in constructing the universe. So I'm actually not sure if I agree with Dirac that progress towards a better understanding of the physical laws goes hand in hand with ever higher mathematics, but that would be a different discussion. In any case, I like the metaphor that the situation could be described by saying that God must have been a mathematician. Now, the modern philosophical discourse is very heavily influenced by another article written by Eugene Wigner, and having a very catchy title, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. So the idea being, or the implication being, that there's something unreasonable and mysterious about the fact that mathematics is so useful and successful in applications in the natural sciences. So one quote from this influential article would be that the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. And I think to try to get to the bottom of this mystery why the laws of physics are written in the language of mathematics. It helps to go back to a time in which the idea of a lawful cosmos was born, at least in the context of Western philosophy. So that's the time of the presocratic philosophers around the 5th century BC. And Detlef always used to say very, very nicely that we must imagine this as a time filled with meaning and purpose. Meaning and purpose through the understanding that we do live in a rational cosmos, that the world is, that there is meaning and sense and lawfulness and rationality to the cosmos, and that we as human beings have, at least to some extent, access to that. And we must start with the great pre-Socratic philosopher Parmenides, because much of the dialectic that shapes the philosophical discourse in the following centuries originates with him. And it's really a dialectic of many deep concepts, that most of which I won't be able to discuss in much detail, but maybe you can take note that we'll be touching at least a bit on them. So the dialectic, the tension or seeming contradiction between being and becoming, between unity and multiplicity, between something eternal and something dynamic or changing, between mind and matter, between experience, so the empirical investigation of the world, and reason. So in Parmenides taught, or one could even say proved, that what is the fundamental being must be uncreated, indestructible, one coherent whole. One path only is left for us to speak of, namely that it is. In this path, there are very many tokens that what is uncreated, it's indestructible, for it is complete, immovable, and without end. Nor was it ever, nor will it be, for now it is, all at once, a continuous one. So when I say that, that he proves, that he argues in a very simple and quite compelling way, basically saying, well, what is, and what is not, is not. So what is cannot be created, because what is cannot come out of what is not, right? And it cannot be divisible, because it doesn't make sense to say that there's a bit of being here and a bit of non-being there, and then more being over here, because again, non-being, what is not, right? So he argues that being what is must be indivisible, uncreated, without beginning or end, a continuous one. And of course, this is not the world that we seem to experience, a world full of diversity and multiplicity and change and motion. But for Parmenides, this is not the true fundamental reality. This is just man's opinions, or how the world seems to us. And so in this poem, Parmenides on nature, there's a theme of two paths. One, the path of truth, right, of this really uncreated, indivisible being, and another path of man's opinion or seemings, in Greek, doxa. And even this work is separated as such. The first, so to speak, metaphysical part is the path of truth. And the second part that deals with Parmenides' natural philosophy and cosmology, right? There's also an important place in his work But in Parmenides' view, this is not a true fundamental being. This is not the path of truth. This is this path of doxa. And this truth, as I said, is obviously not the world that we experience. So indeed, this being, the fundamental real truth, is not something accessible through our senses, but is something accessible through rational thought. Indeed, Parmenides says it is the same thing that can be thought and that can be. And I'm sure you've heard of Zeno's paradoxes of motion, for instance. Zeno was a student of Parmenides and trying to defend his teachings, right? And this is really the point of his paradoxes, because it seems weird now to students, for instance, to tell them Zeno wanted to argue that motion is not possible, right? Obviously, we see motion all the time. And that was actually the reaction, for instance, of the philosopher Diogenes, right? Who, when Zeno thought that motion is impossible, basically said, "Watch me," and started moving, right? But the point of the paradoxes is exactly to show that we cannot think it, that because motion, as Zeno tried to argue, is paradoxical, is something that we cannot really think, and therefore it cannot pertain to aletheia, to truth, to this fundamental being. It's just in this realm of opinion, of doxa. But Parmenides' rationalism goes so deep that he doesn't really make an attempt to save the phenomena. Right? So there's not really an attempt to reconcile what he sees as this eternal, unchanging, indivisible realm of truth, of what is, and the world of our experience. So, kind of as a reaction to Parmenides, Anaxagoras separates this being into mind and matter, leaving something like a cosmic mind that he called the nous as a moving principle in the world that quite literally is the cause of change and diversification. So this nous creates a cosmic vortex that begins to separate the constituents of the world, a bit like in a centrifuge. And this nous is also in us, giving us our mind and our intelligence. So we have here the beginning of a dualism between mind and matter. So this nous separated off, so to speak, from the one coherent, indivisible, eternal being of Parmenides that can explain change and diversification. And Anaxagoras also departs a little bit from this radical rationalism. So one of his most famous fragments is the one saying, "Appearances are a side of the unseen." So Anaxagoras doesn't, unlike Parmenides, doesn't completely dismiss the testimony of the senses, of empirical evidence, but it is something that has to be refined through rational thought. So the appearances are just a side of the unseen, of a deeper, higher truth that has to be reached through the refinement of sense experience by rational thought. So unclear is for instance, how to understand the nous when it comes to the individual and subjective aspects of the mind, something that we might call consciousness. So Aristotle actually criticizes Anaxagoras on this basis for conflating mind and soul. And although Aristotle is often unfair to the presocratics, I think this kind of criticism seems apt. So it's not exactly clear how to think of the nous in terms of something objective versus the subjective and individual aspects of the mind. Heraclitus is very clear on this point, that he's talking about something that is common to all. For instance, here, a very beautiful fragment. The waking have one common world, but the sleeping turn aside, each into a world of his own. So Erwin Schrödinger, so the physicist, who also studied the presocratic philosophers, goes as far as to see in such fragments the idea of an external physical world emerging, basically from the realization that our subjective experiences have a realm of intersection which forms the external reality. Also common to all is what Heraclitus called the logos, the guiding, ordering principle of the cosmos. Like logos is one of these words that's extremely deep and central to Western philosophy, but doesn't have a single good translation into other languages. It can mean word, reason, law, discourse, among other things. So actually, if you know maybe Goethe's Faust, that's also one of the reasons why he despairs, because he tries to translate the Gospel of John, and he doesn't get past the first half sentence. In the beginning, there was the Logos, doesn't know how to translate it. So what is now most commonly translated, in the beginning was the Word, and the Word was with God, and the Word was God. So in Greek, that's also this word Logos. So logos, for the Heraclitean logos, certainly has an aspect of reason and reasoning and rationality, right? But the scholarship has come to the realization that this logos is not something that pertains just to reasoning in the realm of the mind, as something very concrete that pertains to the physical world. So to understand the logos, one must understand Heraclitus' cosmology. For instance, in fragments such as the following: this world order, so cosmos literally means order, which is the same for all, no one of gods or men has made, but it always was, is, and will be, an ever-living fire with measures of it kindling and measures going out. So Heraclitus is often presented as the great antagonist of Parmenides, because Heraclitus sees a world in constant change, a ceaseless cycle of creation and destruction and transformation. So you may have heard the slogan, Pantarei, everything flows, which is not an authentic fragment of Heraclitus, but it's a good slogan for this view of a world in constant change. But even in this constant change, Heraclitus sees something constant, right? This ceaseless cycle of motion and transformation is not an entirely chaotic process, right? But things unfold in certain measures, metra, that in particular the transformation of the elements. So turnings of fire. Fire for Heraclitus was the most fundamental element. First sea, then half of the sea earth, and the other half lightning storm. It spreads out as sea, and its measure reaches the same logos as it was before it became earth. So Heraclitus is also called the Dark One, because some of his fragments seem quite obscure. So this is one of these dark fragments that are not easy to interpret. On the one hand, it's not exactly clear what the meaning of this lightning storm is. So the Greek word is presta, which also doesn't have a good translation. It could mean a form of fire, but it also could mean another element, namely air. And it's also not so clear what the subject of the second sentence is, and therefore what kind of transformation or process he describes here. But probably the transformation of water back into fire. So almost certainly Heraclitus described a kind of cycle process, because that is also something very integral to his view. And it's interesting to note that in this context, if one wants to settle on a translation for the word logos, it has been argued, and I think convincingly so, that the most appropriate translation here would be proportion. So water spreads out as sea, and its measure reaches the same proportion as it was before it became earth. So I believe that what Heraclitus formulates here is the logos as a law of proportion for the transformation of the elements. What he formulates is something like water to earth is like water to storm, and maybe also something like fire to water is like water to earth. So we see already something approaching a mathematical law. And indeed, compared to the nous of Anaxagoras, the logos of Heraclitus is a more abstract, impersonal concept, not something that literally thinks around, right? But something that manifests the order and rationality of this cosmos in such laws that I think are laws of proportion. And it's it's fascinating to jump ahead chronologically to the creationist account giving in Plato's Timaeus, where we find something very similar. So this is a creationist account, meaning it assumes that there is a God, a creator, and Timaeus explains how he created the cosmos. He said, God, in the beginning of creation, made the body of the universe to consist of fire and earth. But two things cannot be rightly put together without a third. There must be some bond of union between them. And the fairest bond is that which makes the most complete fusion of itself in the things which it combines. And proportion is best adapted to effect such a union. God placed water and air in the mean between fire and earth, and made them to have the same proportion so far as was possible. As fire is to air, so is air to water. And as air is to water, so is water to earth. And thus he bound and put together a visible and tangible heaven. And for those reasons, and out of such elements, which are in number 4, the body of the world was created, and it was harmonized by proportion. And Plato also makes more explicit what I can only surmise for Heraclitus, that there's already something numerical, mathematical about this idea of proportion. Now, the nature of the ideal being was everlasting, but to bestow this attribute in its fullness upon a creature was impossible. Wherefore he, the creator, resolved to have a moving image of eternity. And when he set in order the heaven, he made this image eternal, but moving according to number, while eternity itself rests in unity. And this image we call time. So this is so beautiful that it's hard to continue from here. But well, as Whitehead already said, that all of European philosophy is just a series of footnotes to Plato. So I'm continuing with my footnotes on Plato. Also in Plato's epistemology, this idea of proportion plays a very central role. Just to mention very briefly, Plato's analogy of the divided line from Book 6 of the Republic, that's before the more famous allegory of the cave, right? Where he also separates the realm of being into the visible and the intelligible. So the higher form of being that correspond to real knowledge, to episteme, as opposed to doxa, concern this higher realm of beings. And the highest realm that would correspond to true understanding would be the realm of forms or ideas. And mathematics, which is accessible through thought, is somewhere in between this Platonic realm of ideas or eternal forms and the visible world of our senses. And he literally described this again through geometric proportions. So the forms are through mathematical objects, like the visible things are through images of these things, like, for example, a painting or a reflection of a physical object in water. And this idea of proportion even plays a role in Platonian ethics. For instance, here, another Socratic dialogue, Gorgias, where it says, and philosophers tell us, Heraclitus, that communion and friendship and orderliness and temperance and justice bind together heaven and earth and gods and man, and that this universe is therefore called cosmos or order, not disorder or misrule, my friend. It seems to me that you do not put your mind to these things, even though you are versed in them. Rather, failing to observe the great power of geometric equality among gods and among men, you think you should seek for more and more because you neglect geometry. And so this idea of proportions and of geometry is really central to the entire, well, trias of truth, the true, the good, and the beautiful. Now, going back to this fragment 30 of Heraclitus, it may not be obvious that the word measures, metra, already points to something mathematical. But I think it does, and the following definition might help. So two quantities of the same kind are called commensurable if there exists a third quantity, here epsilon, and natural numbers n and m, such that a equals n times epsilon and b equals m times epsilon. Then epsilon is a common measure of a and b, and the ratio of a and b corresponds to the ratio of these rational numbers n and m. Okay, so the ratio or proportion of commensurable quantities corresponds to what we would now call a rational number. So the ratio between two natural numbers and two quantities are commensurable if and only if they have a common measure. And it's important to understand that these quantities or magnitudes are not numbers, right? They would be physical or geometric quantities like length, areas, durations, and so on, right? Only by considering their ratio, by setting them in proportion to one another, we get to something mathematical, something numerical. Also, maybe interesting to note that magnitudes or quantities by themselves, they don't have all the structure of numbers. In particular, two magnitudes of the same kind, for instance, two length or two areas, they can be added or subtracted from one another, right? Just take one line and continue it with a second line, and you get a line that is so-called, that is, so to speak, the sum of the original two, but they cannot be multiplied, right? The closest thing would be, to, for instance, to multiply, to say that a line of 1 meter multiplied with a line of 2 meters would be an area of 2 square meters, but it's no longer a magnitude of the same kind. Right? An ingenious workaround was introduced much later in Descartes' La Géométrie, but it requires us to designate arbitrarily some magnitude as unity. Right? And then, by the intercept theorem, with this arbitrarily chosen unit, right, you have here the relation A is to 1, such as this side x is to b, so x would correspond to a times b. Okay, but this is not really geometric, so it really depends on this arbitrarily chosen unit length. It's a bit like saying the product of 1 meter and 1 meter is again 1 meter, when you could just as well have chosen a different unit, say centimeter, and multiply the same length to 100 times 100 equals 10,000. Right? So it's not something that is really meaningful geometrically. It's only in relation to this arbitrarily chosen unit. And it may be rarely noted that we're committing the same sin, so to speak, when we represent numbers as points on a number line. Per se, there's nothing intrinsically numerical about a linear one-dimensional continuum. Like 2 points have to be more or less arbitrarily chosen as 0 and 1. So to have an origin and some unit length, and only in relation, in proportion to them, can we say that another point on this line corresponds to a certain number. So let's go back to the history of thought. So crucially, between Heraclitus and Plato, we have the Pythagoreans that had undoubtedly a huge influence on Platonic thought and on Plato. And Bertrand Russell even went so far as to say that what appears as Platonism is, when analyzed, found to be in essence Pythagoreanism. So the Pythagoreans were something between a philosophical school and a religious cult. So it's not, except that Pythagoras himself was the founder and leader of the school. It's not so clear how many of the discoveries attributed to the Pythagoreans can be attributed to a historical person of Pythagoras himself. But it was a very influential school. In particular, among this Pythagorean school, there was a group called the Mathematikoi, who were devoted to sciences, so to the scientific investigation of the world. And they had 4 sciences in particular. So arithmetic, just the study of natural numbers, where they discovered nice patterns, such as here, the triangle numbers, for instance, like 1, 3, 6, 10. Then there was harmony, which started, or music, which started as an empirical science. So they noted that chords of different length, right, produce harmonic sounds if the length of the chords stand in certain proportion, right? And in later developed into a more axiomatic theory of harmonic proportion that is still the origin of modern music theory and harmony, so to speak. So there's this very famous painting by Raphael, like the School of Athens, where you have many of the great ancient Greek philosophers. And here is Pythagoras depicted with such a, here is table called the epogdon. And here you see basically the strength representing the different harmonic proportions. Like here 12 to 6 or 2 to 1 would be the octave. And here 4 to 3, the arpente is the perfect fifth. What is 3 to 2 is the perfect fourth. And you have all these proportions also in this triangular number 10 that was considered a holy or perfect number by the Pythagoreans. Right? And then the Mathematikoi, they discovered the same kind of harmonic relations in the motions of celestial bodies. So in astronomy, this is not an accurate picture of the Pythagorean astronomy. They rather had a picture with a great central fire in the center. It was not a geocentric picture. And the planets, the sun, the moon, moving in circles, because that was the most perfect form. And they recognized that also the motions of these celestial bodies occur in certain nice harmonic proportions. And this idea of a music of the sphere would basically culminate 2000 years later in Kepler's Harmonices Mundi. Although the Pythagoreans might have thought that the planets, they literally produce a sound when they move in their planetary orbits. Kepler, of course, didn't believe that anymore. And then, of course, we have geometry, which is maybe the study of proportions in its purest form. Like here, a depiction of the intercept theorem that I referred to earlier. And of course, the Pythagorean theorem is the most obvious examples. But more generally, geometry, Euclidean geometry, is to a large extent the investigation of certain laws that hold, of certain laws of proportions that hold between magnitudes, geometric magnitudes of planar geometry, so length, angles, areas, and so on. And one must understand, so the idea or the characterization of the Pythagoreans, I think, as holding that everything is quite literally made out of numbers, I think is a bit of a caricature that is based on the more esoteric branches of the school. But undoubtedly, number was considered divine and at the core of the order of the cosmos. And only through number is it possible to understand this world order, to understand the cosmos. Here, a quote from the Pythagorean Philolaus. Indeed, it is the nature of number which teaches us all things which would otherwise remain impenetrable and unknown to every man. For there is nobody who could get a clear notion about things in themselves, nor in their relations, if there was no number or number essence. By means of sensation, number instills a certain proportion and thereby establishes among all things harmonic relations. It incorporates intelligible reasons of things, separates them, individualizes them, both in limited and unlimited things. So one must try to feel how sublime and perfect this Pythagorean worldview must have seemed, with all these beautiful harmonic proportions that they discovered in music and in the heaven and in mathematics, to maybe feel the shock that was caused by the discovery of incommensurability, right? That there exist quantities that don't have a common measure. And it's not entirely clear how they discovered it. They might have discovered the more famous Euclidean proof by contradiction. And I think the more plausible and more beautiful option is that they discovered it geometrically. So the Pythagoreans already had an algorithm, today we call it the Euclidean algorithm, to determine the greatest common measure of two like quantities. Like just subtract the smaller from the larger, and then the remaining rest from the smaller, and so on and so forth. Now, if you apply this to try to find the common measure of side and diagonal in a square, you'll find that this Euclidean algorithm never terminates. So in the first step, you have to subtract like the side from the diagonal, leaving here a remainder r. Okay. Now what you can do, you construct from this point P the perpendicular on this opposite side. And now if you draw here the line CQ, you have two triangles that have two sides and one right angle in common. So they are congruent triangles. So you see that you also have this length r here. And now if you continue the Euclidean algorithm, in the next step you have to subtract this remainder r one more time from the side A, right? But this corresponds to subtracting the side of a new square from the diagonal of a new square. So the whole construction, the whole algorithm becomes self-similar and never terminates. Right? So the discovery of incommensurability is in some sense also the begin of the struggle with infinity. And indeed, the Pythagoreans already had a nice algorithm. Instead of going from larger to smaller squares, they basically turned it around, inversed it to go from ever smaller to larger squares. And they were already able to approximate the square root of 2 in a way that converges remarkably quickly. But again, this is something that never terminates. And we know that now what we call the square root of 2 would be just the limit of such a sequence of approximations, right? So the legend has it that Hippasos, the Pythagorean who discovered incommensurability, was drowned at sea by the gods for this blasphemy of destroying this beautiful Pythagorean worldview. Now it's still a big step from here from the discovery of incommensurability to understanding also the ratio, the proportion of incommensurable quantities or magnitudes as a number, what we now would call an irrational number. But I think the step is inevitable. So however, the Pythagoreans had more immediate concern. They first had to save their sciences, in particular geometry, that used to be based on the idea that all magnitudes are commensurable. And the following solution was found by Eudoxos, a student of Plato's, and it's also the basis for book 6 in Euclid's Elements that develops a theory of proportions. So the question is, what does it mean for the ratio of two pairs of incommensurable quantities to be identical? So for two pairs of incommensurable quantities to stand in the same ratio, if this ratio no longer corresponds to a rational number. And Eudoxos' definition is the following, as you'll see, also something that involves infinity, namely something that you would have to test for infinitely many natural numbers. So let A, B, C, D be quantities of the same kind. Then the ratio A and B is equal to the ratio of C and D if for all natural numbers n and m, one of the following three cases holds. Right? So the middle case can only occur for commensurable quantities, but otherwise m times a, if m times a is less than n times b, then also m times c is less than n times d. Or conversely, if m times a is greater than n times b, then m times c must also be greater than n times b. And if this holds one of these three cases for all natural numbers, then we can say that the two ratios are identical. And this is something that works also in the incommensurable case. Okay. So the idea here basically, if we want to take this leap of recognizing also irrational ratios as a number, then a number is something, then an irrational number psi, or any number psi, is such that for all mn, the rational fraction nm is either less or greater or equal psi. And the mathematically trained among you might already recognize that this is precisely the idea behind Dedekind's construction of the reals of the continuum as Dedekind cuts. Right? A Dedekind cut, if all points of the straight line, and here it suffices to consider only rational points, fall into two classes, such that every point of the first class lies to the left of every point of the second class, then there exists one and only one point which produces this division of all points into two classes. That's what we call a Dedekind cut, the severing of the straight line into two portions. So this is exactly the idea that Dedekind picked up, that this is what real numbers do. They divide the rational numbers into two classes. And if such a division exists, then there must also exist a point on the real line, a real number that makes this division, right? But of course, the fact that it took more than 2,000 years from the discovery of incommensurability to the construction of the continuum shows still what a great intellectual, what a monumental intellectual feat it was. In any case, Dedekind himself really emphasized that he was looking for algebraic and not geometric principles to construct the set of real numbers. However, the same ideas and concepts of the Dedekind cut could be used to extend Eudoxus' theory of proportions to a theory of the real numbers with all the structure that real numbers are supposed to have. For instance, multiplications, how would you multiply proportions in the incommensurable case? So don't have to understand here the details, but it's like you would multiply the Dedekind cuts. So it's possible to use these constructions of Dedekind really to understand the set of real numbers as proportions. So numbers as identical to proportion. And all of these ideas, they were still very present at the time of the scientific revolution. Right? For instance, with Galileo performing his acceleration experiment on the inclined plane and reported that he repeated a full 100 times with different distances and times, and we always found that the spaces traversed were to each other as the squares of the times. So what is formulated here is again a law of proportions between times and distances traversed. It's not the algebraic formula like S equals 1/2 GT squared, what we would write down. It's really something understood as and expressed as a law of proportion. Right? Around the same time, Johannes Kepler really combines Platonic and Pythagorean thought with Copernican heliocentrism and formulates his law of harmony for planetary motion. Like the square of the orbital period is proportional to the cube of the semi-major axis of its orbit, for instance. Or that this line joining the orbit with the focus traces equal areas in equal times. Those are all, again, laws of proportion. One generation later, of course, Isaac Newton in his Principia Mathematica showed that Kepler's law, among many others, can be derived, right, from a force law, such that the centripetal force, the gravitational acceleration, is inversely proportional to the square of the distances. So the famous 1/r² laws. But if one looks in the Principia, actually for me, and I would say for many modern mathematicians, it's actually difficult to follow because it's all geometric. It's all Euclidean geometry. There are no algebraic formulas, no differential equation. So Newtonian mechanics is really developed geometrically in terms of such laws of proportions. Even the infinitesimal calculus is introduced as a so-called method of first and last ratios of quantities to apply Euclidean geometry basically to curved lines, to curved trajectories. So Newton had another work, the theory of fluxions, that was an earlier work, but yet unpublished, so published only later, in which he developed a more abstract calculus of infinitesimals and so on. But in the Principia, this is not used. What is used as infinitesimal calculus is, again, purely geometric, this method of first and last ratios of quantity. Actually, in the preface to the first edition of the Principia, Newton himself explained where he saw the connection between physics and mathematics, between geometry and what he called rational mechanics that he wanted to develop. So geometry, he said, is founded on mechanical practice, basically the art of measuring, and is nothing other than then part of universal mechanics, which reduces the art of measuring to exact propositions and demonstrations. But since the manual arts are chiefly employed in the moving of bodies, it happens that geometry is commonly referred to their magnitude and mechanics to their motion. In this sense, rational mechanics will be the science of motion resulting from any forces whatsoever, and of the forces required to produce any motions accurately proposed and demonstrated. Right? So geometry, as understood at that time, and for Newton in particular, is basically the rational investigation of relations that hold between magnitudes, right? And they are directly related to the practical art of measuring magnitudes and quantities in the world. So length, masses, velocities, times, and so on. And indeed, for Newton, the idea is that basically this practical mechanics, the art of measuring, falls short of precise geometry, basically just because of technical inaccuracies, basically just because of the inaccuracies of measurement. So geometry is just this part of the art of measuring that can be reduced to exact propositions and demonstrations. Okay, so what can we learn from that? So when we return to the question, why are the laws of physics mathematical? I want to propose an answer along the following lines. So physics is the science of matter in motion. Regularities of motion manifest themselves in proportions of time, distances, and other geometric or maybe kinematic quantities. Proportions are numbers. I believe I would go so far as to say that these proportions, ratios, are not just expressed by numbers, but they are numbers. So something like pi is the ratio of circumference and diameter of a circle, I think is a genuine identity statement. And numbers are mathematical. Okay. That's why if laws exist, if we do live in a lawful cosmos, this lawfulness will show in certain regularities of motion, right? And these proportions are something numerical and therefore something genuinely mathematical. Now, of course, in modern physics, we employ much higher mathematics and concepts, and it would be a separate discussion what to make of those. So I think my view is both compatible with a selective realism or a full-blown Platonism with respect to this higher order mathematical structures. But my point here is that to formulate the laws of nature and systematize these regularities we see in the world, we might employ all sorts of mathematical structures or objects that we need, but at the end of the day, the theory must make contact to matter in motion, right? And this is where this is where physics meets mathematics conceptually and metaphysically. I also think that with respect to the nature, the metaphysical nature of numbers, this view is a very interesting compromise between Platonism and nominalism. So yes, numbers do exist objectively and mind independently and have their properties and facts independently of us. But at least if space and time are a continuum, numbers are instantiated in the world, right? In the motions of matter, or even in the structure of space and time itself, right? So there's no mysterious separation between some kind of abstract Platonic heaven and the physical world in which we live, right? So numbers are identical to proportions between physical and geometric quantities. So in fact, one of the most, or maybe the most important nominalist project in modern philosophy of science is by Hartree Field, who's trying to do exactly that, to eliminate numbers and reduce everything to relations between, to spatiotemporal relations, or relations between physical magnitudes. For me, just that wouldn't be an elimination of natural numbers. This is exactly of real numbers. This is exactly what numbers are, and why numbers are in the world, but independently of us, and why the lawfulness of the cosmos, if laws exist, would be genuinely numerical. And of course, I'm not saying that we should return to the mathematics of the 18th century and do everything in Euclidean geometry, but it is very easy nowadays to get lost in mathematical abstraction until it appears like a mystery how mathematics could have anything to do with us, or with the physical world, or with physical laws, right? If you think, for instance, about modern axiomatic set theory as the foundation of modern mathematics, and that's of course another great intellectual feat to put it on a sound logical and technical foundation. But then if you start constructing, the natural numbers out of the empty set, so you have the empty set and the set containing the empty set and the set containing the empty set and the set containing the empty set, and so on, construct the natural numbers, and then you construct the integers as equivalence classes of tuples of natural numbers, and the rational numbers as equivalence classes of tuples of integers, and then the real numbers either as equivalence classes of Cauchy sequences of rationals, or as Dedekind cuts. And in the end, you can have the impression that you're only talking about, that all of mathematics is just talking about the empty set, right? So I think this view of numbers as proportions makes much clearer what mathematics have to do with physics and with physical laws. So again, if we do live in a lawful cosmos, then these laws will be laws of proportion for matter in motion, and proportions are numbers, and numbers are mathematical. This presupposes, however, two things about the form and shape of the physical theory that unfortunately can no longer be taken for granted. First, that you have mathematically consistent laws, and second, that you have a coherent and clear ontology, preferably what we now call a primitive ontology, where it is clear conceptually and ontologically how the physical theory relates to matter in motion, right? But I think this view that goes all the way back, at least to the Pythagoreans, and I believe even to Heraclitus, that we can see the logos, the order of the cosmos and the lawfulness of the cosmos and these laws of proportions go a long way towards explaining this apparent mystery of why the laws of physics are written in the language of mathematics, and I believe genuinely mathematical. So it's no accident that this language of mathematics works so well in describing the physical world and the laws of nature. So the real mystery is why the cosmos is lawful in the first place, right? Why are there these nice regularities? And here I want to end with a quote from my teacher Detlef Dürr, from one of his Christmas lectures, where he told students, Well, what is the origin of the law? We could answer, there's no origin. There's a brute fact that everything can be described by a law. And in the end, there's our human law because our senses experience regularities. And we are looking for a code to describe these experiences. And mathematics is a good code that we have developed in a process of trial and error. This is wrong. We are not working like this, at least not as physicists. If we did, we would tear up all kinds of mathematical garbage like a mole tears up a hill in the ground. Galilei didn't do that, Newton didn't do that, and least of all Einstein. To better understand why this idea is wrong, you must understand the mathematical formulation of the law, or better, of the laws that we have discovered so far. It is not a summary of our observations that all bodies fall to the ground. It is not said that some bodies do this and others do that. It is not a bookkeeper's order that we write down. We are looking purposefully for the underlying law of everything. We are guided by ideas of beauty, simplicity, elegance that the law should fulfill, and with these categories we are successful. There's no good explanation for our successes. So, thank you very much. I'm open for questions and comments.
Yeah, first, let's thank you.
Thank you. So thank you very much for this beautiful talk.
I actually don't hear you yet.
Do you hear me now?
Yes, no.
So
Sorry,
thank you
my
very much
speakers
for
just
this-
went out.
for this beautiful talk. So let's open it up for questions. I see that there is one question in the chat. Shall I read it, or do you want to read it yourself, Robert Reniasiewicz?
So I start
Thank you.
the question in the set, in the chat.
In the chat.
May
So-
I? Can you
Yeah.
hear me?
Yes, please go ahead.
Okay, so the question is regarding the Pythagoreans, what is the source that we have for their method of approximations for the square root of 2?
Historically, I believe that what was found in fragments, or maybe archaeologically, is just the first 3 steps or so of this algorithm. And then there were some smart people who reconstructed where it likely came from. I guess it's also a bit of maybe a bit of speculation, but it makes a lot of sense if you have this construction that trying to apply the Euclidean algorithm to find the common measure of diagonal and side length, and it goes to smaller and smaller triangles. So if you take these relations here and inverse them, so to speak, so you think, well, we start with a very, very small square, what we can say, okay, let's say the ratio is about 1 to 1. It doesn't matter if you're very small, and then we get larger and larger. It produces exactly the sequence that converges very nicely and quickly to what we now call the square root of 2. But I'm not a historian, so I can tell you exactly historically and or archaeologically what the original sources
Okay,
were.
when you say archaeologically, does that mean that there is a document, a piece of papyrus or something that has this, or are we getting this through secondarily through the writings of others, of the ancients?
Yeah, that's one of the historical questions that I can't really answer with my authority, with much authority. My source for this is van der Welden, in particular a talk that he gave, The 4 Sciences of the Pythagoreans, but it might also be in his book, Science Awakening. So van der Welden was both, a mathematician and a historian of mathematics. So that is my source. So, sort of the primary historical sources this is based on, I can't exactly tell you. I'm not sure.
Thank you.
Okay, so the next question is by Tim Palmer.
Hi, thank you. Sorry, let me just, yeah, here I am. Thank you for that interesting talk. I wanted to ask a question, or at least pose the thing that bothers me about the mathematical laws of physics. I mean, we clearly, I mean, we only have to look at the world around us to realize that the natural, what you call the natural numbers, the finite integers, play a role. There are a finite number of planets going around the sun. There are a finite number of atoms in a cubic meter of fluid. You know, finite numbers abound. But in your talk, you very much emphasized the real numbers, the continuum.
Mm-hmm.
And, you know, there is no observational evidence that, you know, infinity, this is something that David Hilbert, I think, used to stress, that there's nothing in any of our observations that suggests that infinity, or conversely, the infinitesimal, you know, plays a role in nature. And yet, both in classical mechanics and in quantum mechanics, the continuum is a very vital mathematical object. You know, you wouldn't have theories of either classical or quantum physics without invoking the continuum. Now, the question is, does that mean that the continuum is playing a role in physics, in reality? But if it's not, and this is because I don't believe it is, but the question is then, why is it that laws of physics which invoke the continuum are so accurate in describing what may ultimately be a finite world? I think that that for me is one of the very difficult concepts I can't quite come to terms with, why it doesn't matter that there is, for example, a smaller scale or a larger scale or something, that we can just let things go to infinity and it doesn't really matter. Do you have any thoughts about that?
Yeah, at least to part of the question, I would give the standard, like, realist answer that the best explanation for why this theory is invoking the continuum are so successful is that they're actually true. So that space and time are actually a continuum. But of course, it's possible that it turns out that space and time, the structure of space and time, is actually discrete, and we could maybe do only with natural numbers or rational numbers. And
then we have to explain why the
continuum
continuum is so successful, though, as a concept.
Yeah, I guess then one would give the sort of mathematical explanation that, you know, if you have a theory on a lattice, and then you make the make the lattice distance very small, then these things begin to approximate continuous quantities and derivatives and things like that. But I think that even in this case, I think that this perspective that also rational numbers are literally ratios, proportions, or identical to ratios, proportions of geometric and physical quantities is helpful to dissolve at least part of the mystery. So there's no gap between some abstract set theoretic objects that exist in some Platonic heaven and matter moving in physical time and space. So the proportions that we find in this motion of matter in space and time, be it continuous or discrete, is genuinely numerical and therefore mathematical. I hope that helps. I hope that helps.
Yeah, I don't want to prolong the discussion, but I think when you make the statement that as this lattice shrinks, it's somehow the effect is to make the result less and less dependent on the size of the lattice. That evokes certain assumptions, I think, metric and measure assumptions, which then raise in my mind the question, why? Why do those assumptions work? And it's not obvious, I don't think.
Yes.
But anyway, thank you very much. I don't want to prolong the discussion.
Yeah. No, I think conceptually that would just be the idea. If it turns out that really in reality, fundamentally space and time are discrete, there would have to be some explanation of why continuous approximations work, and it would be something along those lines. Of course, and the details can get arbitrarily complicated. Like if you could show that certain continuum limits exist for like quantum field theories on a lattice, you would probably get a Nobel Prize or a Fields Medal or whatever. But I think that would be basically the idea.
Thank you.
Okay, so we have another question by C. Perry.
Great. Oh, can you hear me?
Yes.
Yeah.
Okay, great. So thanks for this talk. I'm really sympathetic to a lot of parts of this project. I mean, I would honestly go so far as to say I maybe am advocating that we should return some of our mathematical and physical practice to the way it was being done in the 18th century. But setting aside some of that talk, I'm curious about specifically what is being added to the picture by the claim that proportions are numbers. So imagine for a minute, right? Somebody offering an alternate explanation where they say something very similar. Someone asks, well, why are the laws of physics so mathematical? Why are they written in the language of mathematics? And someone says, well, look, physics is the science of matter in motion. These regularities, they've got these proportions that hold between distances and all these other different quantities. And those proportions are just ratios. Also, numbers are way easier to write down than most physical quantities because they fit on paper. We have glyphs for them. And those things also stand in ratios. And so we use those, and we use those when we're writing it down. That's an account at least that like gets at why it's written that way, even if it doesn't claim that they're mathematical in any other sense besides having ratios. But it still feels like if there was any additional mystery, the mystery is like, well, why is it that there's this thing ratios had by both the stuff in the world and the numbers? And it's not clear to me that like the mystery goes away by saying that, oh, actually, no, it's the numbers are those things. Like that.
But
I mean, in the case of numbers, the reason they stand in those ratios is kind of we've posited that they are that way. And as we've come up with what those numbers are like, and we've discovered how they work, and then those other ratios in terms of space, these are supposed to be, what Euclid thought was like discovering the structure of the space we are in fact in, not.
Yes. No, I just think that if you say, well, two numbers can stand in a certain ratio, and two distances, let's say, can stand in a certain ratio, what is the same? And you say they are the same or identical. What is the same is already something genuinely numerical. So the ratio of two lengths or of two areas or of two masses. So the ratio or proportion of any two like quantities is already a number. So I think it would be. I mean, from my point of view, it would be redundant.
You just mean by is a number here. You just mean. There is a number that stands in that ratio to the number one.
No, I mean the ratio is a number. I just don't think there's a need for this distinction to say, well, there's a ratio between numbers and there's a ratio between physical magnitudes, and they are somehow, if you write an identity sign between them, I think metaphysically what you have on both sides of the identity claim is the same kind of entity, namely a number. So I don't think you otherwise you just add an additional layer of, well, if you say these ratios are different things conceptually and or metaphysically, so what does the identity statement what does the identity statement refer to? But the other thing is that the other thing is that well, there are things that many philosophers worry about, and either one kind of shares this worry or doesn't even understand what the problem is. If the relation between, proportions of physical magnitudes and number is not identity, then there's always a question of, well, what is this metaphysical? What is this metaphysical relations? Like if numbers are objects of set theory or structures or whatever that exist in some Platonic heaven, what is the kind of relations that connects them to these regularities of motion in the physical world, right? And I think that there's no gap. They are identical. So these proportions between physical quantities or geometric quantities, there are numbers. There's no need for an additional relation of, I don't know, grounding or instantiation or anything else that one might find metaphysically objectionable. They are just numbers.
So I'm this is just a tiny last. I don't see exactly what it feels like, having given this beautiful sort of historically oriented talk. You would be especially bothered by like a gap between the status of numbers and these other things going on in the world. It took us until Dedekind to show that the arithmetic side of mathematics had enough going on in it to be able to capture in a rich way all of the different kinds of proportions all on its own, right? That was something that you sort of said that, like, oh, we could try to get some of Dedekind's benefits for geometry, but the whole point was that Dedekind was like, we already have a really, really rich account of how proportion and ratio works in geometry. What was hard and was a genuinely amazing thing to discover was that you couldn't really do it with arithmetic all on its own without just being kind of parasitic off of the geometry. But what I'm wondering is, like, well, why would you then sort of push so hard on this? I mean, if this was an identity that was such a clear, like, that it was clear that just if there's such a thing as ratio, those things are like numbers, you would either think that everyone would have been trying to do the Dedekind thing, or that Dedekind would have been alive and doing that thing many hundreds of years earlier. It seems like that's the
yeah. I mean, for Dedekind himself, he even made a point of the fact that doesn't want to do geometry, that he's looking for purely algebraic principles. And of course, that was if you have such an algebraic calculus, it's very convenient, but I think you begin to lose track the more and more you get into this abstract calculus of what it has to do with the physical world. So I think, and this is where the geometric picture and understanding numbers of proportion closes a gap metaphysically, but also epistemologically. Right? So I think, for instance, if you understand the Dedekind cuts purely as a construction in set theory, my claim would be, well, okay, the whole set theoretical formalization is an extremely useful abstraction, but the real thing is about proportions of magnitudes that are in the world, that are genuinely physical. But so yeah, I hope. Thanks.
If you're fine, yeah, then I think it would be the time to move on to the next question by Barry. So please, Barry, go ahead.
Yeah, hi. Am I audible?
Yes.
Can you hear me? Okay, good.
Not visible, but
Can't see me, though,
okay.
because my camera's broken.
Oh.
I'm sorry. Anyway, Dustin, that was a beautiful talk. I very much appreciate it, especially the last quote from Detlef. It sounded very much from that quote that Detlef thought that it was just a mysterious fact that our universe is simple enough to be mathematically describable, and that whether you're a Humean or a non-Humean about laws, is orthogonal. Being a non-Humean won't help explain why it is that the universe is describable by mathematics. And I think that's right. However, I think being Humean about laws may do something to help explain the role of mathematics, because we introduce on the sort of the general systematizing conception of what we're doing with laws is we introduce into our language expressions which help systematize the fundamental facts. The fundamental facts that they have this certain structure that enables them to be described by mathematics, well, that's a mystery. That's the brute thing. But the role of mathematics is, as, for example, Lewis suggests in his discussion of probability, to systematize the fundamental facts. So I think that's close to your picture, but not exactly the same, and bring in more towards another kind of picture, which I prefer. Does that make sense?
I think so, yeah. And I think I don't even want to disagree, even though, as you know, I'm not a Humean. But I think that one could certainly say that some of these concepts, like some of the concepts like forces, maybe even velocity, acceleration, energy, whatever, are to some extent concepts that we introduce to systematize the world. But I think that the point of view that I advocated for would still explain why ultimately the laws that we formulate would be formulated in mathematical language and even be genuinely mathematical, right? So I don't want to go so far, or I would find it very, very unsatisfying to go so far to say that, well, even mathematics just works so well because it's something that we invented to be useful in systematizing the world. So that's not my view. So my view is that
I saw that. I understood that. I was suggesting an alternative, more of a nominalist view along Field's lines, that mathematical language is introduced in order to systematize the physical facts.
Yes, some of the language, I think, certainly. So I'm not sure if I want to. So I'm not sure if I want to be realist about, I don't know, C-star algebras or tensor bundles or whatever. I'm not. I have to think about that. But I think that at the end, where rubber meets the road, if one agrees that physics is ultimately the science of matter in motion, that regularities in motion would have to show up in certain proportions of physical quantities, and that these regularities are therefore in the end genuinely mathematical.
Yeah, I think what I'm saying is an agreement with that, but we'll have time to discuss this more later. Anyway, but thanks for the talk. It was really nice.
But then the last mystery that Detlef, I think, formulated so nicely in Humean terms would be, why should there a best systematization? Why should there be a good systematization to begin with? Right. That's sort of the mystery.
Right.
Why is nature so kind to us? In Leucian terms.
When we're so unkind to it, it's amazing.
Right. That's true.
Okay, great. So there's another question by Sahand. Sahand.
Hi, Dustin. Thank you for the talk.
Hi, Sahand.
I wanted to ask, so one part of this talk was that you defined numbers as proportions. And then one natural question could be, how do you define proportion?
How do you define proportion?
Yes.
I'm not sure what exactly this is. I'm not sure what exactly this is asking for.
You can make this question more exact. So if the quantity we are looking at are lengths, what does it mean? Proportion of two lengths? What does that mean?
Yeah, how one length is to the other. And
yes.
But I mean, it's important that you get something numerical once you consider the proportion. So there's no sort of absolute intrinsic length that is already quantitative or numerical, and then you can divide, but you get to something quantitative or numerical just by considering the ratio or proportion of two like quantities.
Okay.
And of course, basically the original definition is the nice simple one that you can give of what a ratio is or what a proportion is in the commensurable case. Where was it? So for two commensurable quantities, right, there exists a common measure, right? And if you can say then the first quantity is n times this measure, say you just have n, you have like a unit length that is your common measure, and you n times together and m times for the other, then the ratio corresponds to this number n to the ratio of this two number or the rational number and divided by m. Of course, the things get very subtle because incommensurability exists, right? And then we just have this more abstract identity criterion due to eudoxos, where maybe it's less clear as a definition of proportion in the incommensurable case. It's more an identity criterion of proportions in the incommensurable case. So I see that there's still an interesting question there. But this is basically the commensurable case would be the prototype, and also good to illustrate this point that the magnitudes themselves are not numerical, only their ratios.
Okay, yeah, thank you.
Okay, so we have one more question. Let us take this as the final question. It's by Angel Garcia. John.
Hi, thank you. The question is, what about the division by zero? For instance, 1/0 is a proportion, but what would be the number? Perhaps it's a silly question, but I'm eager to see what the solution in this case. And the other question is whether for every number we have a proportion, and if so, what about other numbers, like, for instance, transfinite numbers and Grassmann numbers and all that?
Yeah. So the first question I'm not sure I understood about the division by zero. I mean,
yeah, it's a proportion. You have quantity of something, and you are making a ratio with a null quantity of other things.
well, of course, usually no, division by zero is not defined, and I think this view of proportions makes clear why it is not defined, because a magnitude of zero is no magnitude at all, at all.
So there will be no number for this proportion.
Yeah, but I think, no, at least in standard mathematics, there's no number corresponding to 1 divided by 0. So the second question, oh, okay, now Z is asking a pretty challenging question. What about a mass of 0, which it kind of exists, massless particle? That's a tricky one. I don't have a good answer for that. I'm afraid I also don't have a good answer for your second question. What about Grassmann number or transfinite numbers? I was actually afraid that someone starts asking me about complex numbers, where already it gets tricky. So I'm not sure what to think, both about the metaphysical status and the physical relevance of these kind of numbers. So obviously, this is something that the study of mathematics, qua mathematics, leads you to more or less naturally, right? Once you have algebraic equations to get to complex number, once you have set theory, try to construct transfinite numbers. But yeah, then
Thank you so much for
the
your
story I'm trying to say, to tell about real numbers and why they matter to physics and physical laws, yeah, that it doesn't naturally extend to that. Yeah.
Okay, thank you.
Thanks. So I think there is no further question. So then let us thank Dustin again, and let's end here.
So thank you too also for the interesting and challenging questions. And again to the organizers.
Yeah, thank you, Dustin. It was really a pleasure having you. Maybe a short announcement. I mean, whoever is up for it. Next week, we're going to have our next speaker, Daniel Sudarsky. So he will talk about dynamical reduction models, especially in the general relativistic context. We're going to have, I think, part of the talk at the NMU. So
yes.
Whoever is here in Munich is of course, very warm welcome to join us. But we'll also try, like last time, with Daniela Lazarovici to stream it. And yeah, would be happy to have you also next section. All right. Paula, do you still have some final words?
But your final words, I think.
Okay, then
thanks.
Thank you all. It was a pleasure to have you all, and hopefully see you next week.
Thank you. Bye.